About 13.8 billion years ago, the entire cosmos consisted of a tiny, hot, dense ball of energy that suddenly exploded. That's how everything began, according to the standard scientific story of the Big Bang, a theory that first took shape in the 1920s. The story has been refined over the decades, most notably in the 1980s, when many cosmologists came to believe that in its first moments, the universe went through a brief period of extraordinarily fast expansion called inflation before settling into a lower gear. That brief period is thought to have been caused by a peculiar form of high-energy matter that throws gravity into reverse, inflating the fabric of the universe exponentially quickly and causing it to grow by a factor of a million billion billion in less than a billionth of a billionth of a billionth of a second. Inflation explains why the universe appears to be so smooth and homogeneous when astronomers examine it at large scales. But if inflation is responsible for all that can be seen today, that raises the question, what, if anything, came before?
Why the universe began in the way that it did, if indeed it had a beginning.
Trillion of them in the piece of the universe we can see.
For some, that leaves the door open for a divine creator, a great pumpkin who lies outside of time and space. But it could also be asking what existed before the universe is a nonsensical question, like asking what is north of the North Pole. Although effects within the universe have causes, the universe as a whole may not have or need one. But that answer doesn't feel very satisfying, and the famous physicist Brain Cox can sketch out some possible scenarios.
So if the universe is eternal, and it might not have had a beginning, if it's eternal, what place is there for a creator?
Imagine that the universe we observe, from end to end, is just a drop in the cosmic ocean. That beyond what we can see, there's more space, more stars, more galaxies, and more everything, for perhaps countless billions of light years farther than we'll ever be able to access. And that as large as the unobservable universe is, that there are again innumerably more universes just like it, some larger and older, some smaller and younger, dotted throughout an even larger spacetime. As rapidly and inevitably as these universes expand, the spacetime containing them expands even more quickly, driving them apart from one another and ensuring that no two universes will ever meet. It sounds like a fantasy picture, the scientific idea of a multiverse. But if the science we accept today is correct, it's not only a valid idea, it's an unavoidable consequence of our fundamental laws.
So there are lots of multiverses, actually, in physics. One of them is called the inflationary multiverse, which is we have a theory of essentially what happened before the Big Bang.
The idea of the multiverse has its roots in the physics required to describe the universe that we see and inhabit today. Everywhere we look in the sky, we see stars and galaxies, clustered together in a great cosmic web. But the farther away in space we look, the farther back in time we look as well. The more distant galaxies are younger and hence less evolved. Their stars have fewer heavy elements in them. They appear smaller as fewer mergers have happened. There are more spirals and fewer ellipticals, which take time to form from mergers, and so on. If we go all the way to the limits of what we can see, we find the very earliest stars in the universe, and then a region of darkness beyond that, where the only light is the leftover glow from the Big Bang. But the Big Bang itself, occurring everywhere at once, some 13.8 billion years ago, wasn't the start of space and time, but rather the start of our observable universe. Before that, there was an epoch known as cosmic inflation, where space itself expanded exponentially, full of energy inherent to the fabric of space-time. Cosmic inflation is itself an example of a theory that came along and superseded the one that came before it, in that it was consistent with all the successes of the Big Bang and encompassed all of modern cosmology. It explained a number of problems that the Big Bang couldn't address, including why the universe was the same temperature everywhere, why it was so spatially flat, and why there were no leftover high-energy relics like magnetic monopoles. And it made many distinct new predictions that could be tested observationally, most of which have been confirmed. However, there's also one consequence that inflation predicts that we do not know whether we can confirm or not: the multiverse. The way inflation works is by causing space to expand at an exponential rate. This takes whatever existed before the hot Big Bang and made it much, much, much larger than it was previously. So far, so good. This explains how we get such a uniform, large universe. When inflation ends, that universe gets filled with matter and radiation, which is what we see as the hot Big Bang. But here's where it gets weird. In order for inflation to end, whatever quantum field is responsible for it has to roll from the high-energy, unstable state that drives inflation down into a low-energy, equilibrium state. That transition and rolling down into the valley is what causes inflation to come to an end and create the hot Big Bang. But whatever field is responsible for inflation, like all other fields that obey the laws of physics, must be an inherently quantum field in nature. Like all quantum fields, it's described by a wave function with the probability of that wave spreading out over time. If the value of the field is rolling slowly enough down the hill, then the quantum spreading of the wave function will be faster than the roll, meaning that it's possible, even probable, for inflation to wind up farther away from ending and giving rise to a Big Bang as time goes on. Because space is expanding at an exponential rate during inflation, this means that exponentially more regions of space are being created as time goes on. In a few regions, inflation will come to an end, where the field rolls down into the valley. But in others, inflation will continue on, giving rise to more and more space surrounding each and every region where inflation ends. The rate of inflation is far more rapid than even the maximum rate of expansion of a matter and energy-filled universe. So in very short order, the inflating parts take over everything. According to the viable mechanisms that give us enough inflation to produce the universe we see, there are many more regions of space surrounding our own, where inflation did end, where inflation doesn't end right away. This is where the phenomenon known as eternal inflation comes from. Where inflation ends, we get a hot Big Bang and a universe, of which we can observe part of the one we're in, very much like our own. But where inflation doesn't end, that produces more inflating space, which gives rise to some regions that will have hot Big Bangs causally disconnected from our own, and other regions that will continue to inflate. And so on. This picture of huge universes, far bigger than the meager part that's observable to us, constantly being created across this exponentially inflating space, is what the multiverse is all about. It's important to recognize that the multiverse is not a scientific theory on its own. It makes no predictions for any observable phenomena that we can access from within our own pocket of existence. Rather, the multiverse is a theoretical prediction that comes out of the laws of physics as they're best understood today. It's perhaps even an inevitable consequence of those laws. If you have an inflationary universe governed by quantum physics, this is something you're pretty much destined to wind up with. It's possible that our understanding of the state before the hot Big Bang is incorrect, and that our ideas about inflation are completely wrong for this application. If that's the case, then the existence of a multiverse isn't a foregone conclusion, but the prediction of an eternally inflating state, where an uncountably large number of pocket universes are continuously born and driven inextricably apart from one another, is a direct consequence of our best current theories, if they're correct. So, what is the multiverse? It may go well beyond physics and be the first physically motivated metaphysics we've ever encountered. For the first time, we're understanding the limits of what our universe can teach us. There is information we need, but that we'll never obtain, in order to elevate this into the realm of testable science. Until then, we can predict, but neither verify nor refute. The fact that our universe is just one small part of a far grander realm, the multiverse. While many things remain unknown, there are some way to get to somehow the multiverse. But to do that, we have to start with just the universe. By definition, the universe is all the things. It is the sum total of complete physical existence. If it's a thing, it's in the universe. But even with that definition, we can start to crack the door to other universes. One way to do that is to recognize that the universe is only so old, and light can only travel at a finite speed. So there's a limit to what we can observe in the universe. That limit is about 45 billion light-years away. However, that explanation gives you a very weak vision of the multiverse. Actually, there's more to the universe than what we can observe. So there's more stuff out there, more stars, more galaxies, maybe even more intelligent creatures than we could ever make contact with. All of these things are in the universe, but are definitely not a part of our own world. In the multiverse, our universe is merely one of an infinite chain of universes. Imagine a giant foam, like the top of a bubble bath. The multiverse is the foam itself, always growing and always creating new bubbles, with each bubble acting as its own independent cosmos. All of these bubble universes exist within the same framework of space-time. If you point your finger in any random direction, somewhere out there, past some unfathomably huge distance, is another universe, and beyond that, another, and beyond that, another. If this kind inflation truly never ends, then there are an infinite number of universes out there in the multiverse. Each one of those universes could have ended their local inflation in the same way. But it's also possible that as each universe pinched off, it got a brand new set of physics to go along with it, with different collections of forces and particles. Some of those universes would look incredibly similar to our own. Others may have failed, full of nothing but void. Some may be far stranger than we can possibly imagine, and some may be exact replicas of us. If, and this is a big if, there are only a finite number of ways to arrange all the particles in a given universe, then with an infinite number of universes, you're bound to get repeated copies. That means that not only is there another universe out in some random direction, but that if you follow that line far enough, you'll encounter a duplicate of you doing the exact same thing, right now, in this present moment. This is all pretty wild, but difficult to test. The problem is that all the bubbles of the multiverse are completely inaccessible from each other. They exist, but not in any connected way. So we can't just get in a rocket and fly off to head to our nearest neighbor. But there may have been some cosmic accidents in our ancient past. When our universe was younger, it had just broken off from the larger inflation-driven flow. If another bubble universe just happened to nucleate close to ours, then there's a small chance that our universes may have briefly intersected before being permanently driven away from each other. The chances of that happening are incredibly small, but not zero, which provides a way to test the multiverse. Unfortunately, no observations of the larger cosmos have revealed any indications that we have suffered such a collision. While those experiments don't rule out the multiverse idea, they don't exactly help. The only thing left we have to go on is our theoretical understanding of the early universe, which we don't really understand. We have only a vague picture of what inflation is like. We do not know what powered it, why it had the energies that it did, or why it shut off in our cosmos. We don't even know if inflation automatically leads to a multiverse, or if we're misunderstanding our own math. But while physicists continue to debate the idea, it does make for a good story. But put multiverse aside, we have some alternatives, one of which is known as the cyclic universe model, and it argues that our current observable universe is part of a series of universes. Our universe is currently expanding because of the Hubble parameter, and if that parameter stays constant, it will expand forever. But if the Hubble parameter is cyclic, then the universe will start contracting at some time in the future. It will contract until it reaches a new hot dense state, a new Big Bang for a new universe. A cyclic universe needs no beginning. It always was, always is, and always will be. But the model isn't without its problems. One of the main ones is the problem of entropy. Entropy is a measure of disorder in a system, and according to the laws of thermodynamics can never decrease. In a simple cyclic universe model, the entropy of any given universe must be at least a little greater than its parent universe. So, if universes cycle to an infinite past, the current universe would have infinite entropy, which it doesn't. So there must have been some initial universe with low entropy, and we're back to the beginning. There is a way to get around this problem. The universe could have an overall scale factor. If that scale factor increases with each universe, then the entropy problem goes away. What's interesting is that this scale factor is conformally invariant. This means it doesn't change how the universe appears. Each universe might be twice as big as the previous one, but everything within that universe scales by the same factor. If you double the income of everyone on the planet, but also double the cost of everything, then nothing has really changed. This conformally invariant scale factor allowed the cyclic universe to exist without a beginning. Each universe has a cause, and it's turtles all the way down. But a new study has found a flaw in this idea. The team looked at the mathematical structure of cyclic universe models within general relativity and found that all of them are geodesically past incomplete. In other words, within the bounds of general relativity, you cannot trace a universe like ours back through an infinite cycle of universes. There may have been a vast number of universes before ours, but there must still have been a first universe. So the cyclic universe model can provide a cause for our universe, but it only kicks the problem of beginnings down the road. Even if our universe wasn't the first, some universe was. At least for the usual cyclic universe models. As the authors point out, their work doesn't apply to conformal cyclic cosmology proposed by Roger Penrose. In that model, the scale of each universe is infinitely larger than the cycle before. The authors plan to look at that model next, and thus begins a story for another time. Another approach involves M-theory, which is a unifying framework in theoretical physics that attempts to combine the various string theories and supergravity into a single, coherent theory. It is considered one of the most promising candidates for a theory of everything, which aims to describe all fundamental forces and particles in the universe within a single, all-encompassing framework. The M in M-theory has been interpreted in various ways, including membrane, magic, mystery, and matrix, reflecting its complex and somewhat enigmatic nature. M-theory has profound implications for cosmology, the study of the origin, evolution, and eventual fate of the universe. One of the most significant contributions is the idea of the multiverse. In M-theory, our universe could be one of many universes, each with its own distinct physical laws and constants. These universes might be connected through higher dimensional spaces and could interact in ways that might be observable, such as through gravitational waves or other cosmic phenomena. Another intriguing aspect of M-theory in cosmology is the concept of brain-world scenarios. In these models, our four-dimensional universe is viewed as a three-brain embedded in a higher dimensional space. This perspective can provide novel explanations for various cosmological observations, such as the nature of dark matter and dark energy, the hierarchy problem, and the initial conditions of the Big Bang. Despite its elegance and potential, M-theory is not yet fully understood, and many of its mathematical formulations and physical predictions remain speculative. One of the significant challenges is the lack of direct experimental evidence, as the energy scales at which M-theory's effects become apparent are far beyond the reach of current particle accelerators. Researchers continue to explore the mathematical structure of M-theory, develop new computational techniques, and search for indirect evidence through cosmological observations. Advances in technologies like gravitational wave detectors and space-based telescopes may eventually provide the necessary data to test M-theory's predictions. In summary, M-theory represents a bold and ambitious step toward a unified understanding of the fundamental nature of the universe. While it is still a work in progress, Its potential to reconcile the different forces and particles within a single theoretical framework makes it a central focus of modern theoretical physics and cosmology. In the end, we have to admit we're ignorant about the true beginning of the universe. And even if we lean towards an eternal multiverse with no real beginning at all, we don't know why there is something, or, more to the point, why there is everything instead of nothing. In other words, the universe is simply too complicated for humans to ever understand completely. And not only is it confusing, space is teeming with celestial wonders, some of which are breathtakingly beautiful and others that are scary. Our fear often stems from our limited understanding of cosmic phenomena. Here are 7 of these unsettling cosmic entities or phenomena. 1. Dark matter. Dark matter is an elusive form of matter that makes up around 30% of the matter energy of the observable universe. Despite this, we don't know much about it. First proposed in the 1930s by Swiss astronomer Fritz Zwicky, dark matter wasn't initially widely accepted. It was in the 1970s that Vera Rubin provided compelling evidence for its existence by studying the rotation of galaxies. One of the most baffling things about dark matter, which makes it so elusive, is that it doesn't emit, absorb, or reflect light. This means it can't be directly observed, and we can only infer its existence through its effects. Despite this, dark matter interacts with regular matter via gravity. This is why it can influence galaxy clusters' formation, impact galaxies' rotational speed, and cause gravitational lensing. Scientists have proposed several potential dark matter particle candidates, such as weakly interacting massive particles, WIMPs, axions, and sterile neutrinos. WIMPs are currently the leading candidates for dark matter particles due to their weak interactions with regular matter and their potential detectability through rare collisions. Not knowing such a large part of the universe's mass is unsettling and raises questions about the fundamental nature of reality. This is what makes the search for dark matter so exciting, necessary, and terrifying. 2. Rogue black holes. Black holes are formed from dying stars undergoing gravitational collapse after exhausting their nuclear fuel. They have the strongest gravitational pull of any object in the universe. Black holes come in various sizes and, most of the time, are found at the center of a galaxy. But that's not to say that most are located there. As mentioned before, nothing can escape its gravitational pull, not even light. But if a black hole at the center of a galaxy is terrifying, imagine a black hole wandering through space untethered. This is called a rogue black hole. These black holes are not gravitationally bound to any galaxy, meaning they roam through space independently. They are a result of an incomplete merger when two galaxies collide. One of the only rogue black holes directly detected was in January 2022 using the Hubble Space Telescope. This isolated stellar black hole, named Ogle 2011 BLG 0462, is 5,000 light-years away and possesses a mass approximately 7.1 times that of the Sun, moving with a speed of around 45 km/s. If a rogue black hole were to approach our solar system, its gravitational pull could upset all celestial objects, including the Sun and the planets. That being said, given the enormous distances separating stars and the uncommon nature of rogue black holes, the likelihood of such an event is extremely rare. 3. Zombie stars. Supernovas are massive explosions that occur towards the end of a star's life. They release much energy that may temporarily outshine entire galaxies. Supernovas often leave behind remnants like neutron stars or black holes. There are many types of supernovas, of which type 1a is interesting. These are seen in binary systems, where a white dwarf accumulates matter from its companion, leading to a catastrophic explosion with a consistent luminosity. Scientists have proposed a subtype called type 1ax supernovae, which have lower luminosity and ejection velocity than type 1a. The remnant of this type of supernova is a zombie star. These stars are generally hard to observe as the supernovas are rare events. A milestone achievement was the observation of supernova SN 2012Z, a type IAX supernova, the first identified star system observed before going supernova. Apart from this, supernova SN 1181 was observed as early as 1181 AD by Chinese and Japanese astronomers. Modern astronomists, including Dana Patrick, later linked SN 1181 to the nebula PA30 and the central star IRAS 00500 plus 6713, a now confirmed zombie star. IRAS 0500 plus 6713 is the only one known in the Milky Way. The fact that so little is known about zombie stars contributes to the eerie fascination surrounding them. Additionally, its unconventional characteristics, such as its formation and implication for stellar evolution, add to it, although the name isn't really indicative of anything. 4. Galaxies without dark matter. Dark matter is typically considered the invisible glue that holds galaxies together, but scientists have observed galaxies having much less dark matter than expected. DF2 and DF4 are galaxies with very low velocity dispersions, indicating little or no dark matter. This discovery challenges conventional theories of galaxy formation and evolution, as galaxies are thought to form within vast halos of dark matter. One study suggests that these galaxies formed due to high-velocity collisions of gas-rich galaxies, similar to the collisions that created the Bullet Cluster, but on a smaller scale. In this scenario, gas separates from dark matter during the collision, and subsequent star formation creates dark matter-free galaxies. The Hubble telescope has been used to measure these galaxies accurately, but none explain the missing dark matter. So the question that needs to be answered is, if not dark matter, what holds these galaxies together? 5. Boomerang Nebula. The eastern Antarctic Plateau in Antarctica is the coldest place on Earth, which is 3 times warmer than the universe, the Boomerang Nebula, making it one of the most terrifying places in space. The Boomerang Nebula, sometimes called the Bow Tie Nebula since it resembles a bow tie, is situated in the constellation of Centaurus. It is the coldest known place in the universe, with an astonishing temperature of 1 Kelvin or 272.15 degrees Celsius. The Boomerang Nebula is classified as a protoplanetary nebula, thought to be a star system progressing toward the planetary nebula phase, the final stages of stellar evolution. Scientists believe that the nebula's central star is a dying red giant, which is causing an outflow of gas, leading to the continued formation of the nebula. This outflow creates an hourglass shape, visible due to the illumination of dust by starlight. In 1995, using the ESO submillimeter telescope in Chile, astronomers measured its temperature as 1 degree above absolute zero, making it colder than the background radiation from the Big Bang. The extremely low temperature of the Boomerang Nebula challenges scientists' current understanding of how energy is balanced in space. It's colder than the background radiation from the Big Bang, raising questions about the mechanisms and processes at play here. It is terrifying to imagine how cold this place could be. Brr. 6. Strange matter. We know about ordinary matter, which makes up the things around us, and we've discussed dark matter, but there is another type of matter called strange matter. Strange matter is made of strange quarks, a type of fundamental particle. It is hypothesized to occur in extreme environments, such as the core of neutron stars, or as isolated droplets, known as strangelets, ranging in size from femtometers to kilometers. Scientists propose that strange matter could be created when nuclear matter is compressed beyond a critical density, which dissociates protons and neutrons into quarks. This hints that strange matter is only stable at high pressures. The strange matter hypothesis suggests that quark matter is the true ground state of all matter, making it more stable than ordinary nuclear matter. This idea is also known as the Bodmer-Witten assumption. Researchers constantly seek observable signatures to identify whether neutron stars have quark matter in their core. They call this type of neutron star a hybrid star. While strange matter is a fascinating theoretical concept, much of its understanding is based on predictions and models. There is no physical evidence supporting its existence, making it truly strange. 7. Near-Earth objects. The solar system is filled with random celestial objects like asteroids and comets, some of which are capable of approaching the Earth during its orbit. This means some of them could affect the Earth and its systems. These objects, called near-Earth objects, or NEOs, are small solar system objects that can have close approaches to Earth when their orbits intersect or come close to Earth's orbit. Scientists have observed 23 comets that have passed within 0.1 AU, or 149.6 million kilometers of Earth. Some recent examples are asteroid 2020 VT4 in 2020 and asteroid 367943 Duende, 2013, which passed closer than satellites in geosynchronous orbit. One of the closest encounters was the 1972 Great Daylight Fireball, which passed within 58 kilometers of the Earth's surface. This makes NEOs one of the most terrifying things in space for all living things on Earth. Apart from disrupting connections, NEO impacts can also result in explosions in the upper atmosphere or on Earth's surface, creating tsunami waves or craters. Scientists have also sent spacecraft to NEOs to collect samples to study their composition and have a better understanding of their origin. Projects like SpaceGuard surveys and the Planetary Defense Coordination Office have been set up to detect, track, and assess NEOs. This enables early warnings and developing strategies for potential deflection or mitigation. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.